Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic nMOS inverter and pull-up to pull-down ratio of an nMOS inverter driven through another nMOS inverter. Going into the details. By the completion of this topic, you will be able to derive the pull-up to pull-down ratio of an nMOS inverter driven by another nMOS inverter. So, when you have an nMOS inverter, so what is meant by an nMOS inverter we will see in the next slide. So where the pull down network will be an nMOS inverter and pull down will also be an nMOS inverter but an enhancement mode. So when this is driven or whether this is if this is driving one more nMOS inverter like this, so what is the pull up to pull down ratio? We call it as ZPU by ZPD. That we are going to see. So basically the nMOS inverter. What is an nMOS inverter? Basic requirement for producing a complete range of logic circuits is the inverter. That should be known. For any range of logic to be generated, the basic requirement is an inverter, or otherwise we call it as NOT gate in digital logic. The basic inverter circuit requires a transistor with source connected to the ground and a load resistor connected from drain to the positive supply rail VDD. So like this, basic inverter construction should be, it should include a transistor that can be this is a MOSFET based inverter. So transistor here refers to nMOS. Then it's a source terminal. The source terminal should be connected to the ground and its drain terminal should be connected to the supply through a load resistor actually. But in fabrication of the devices or fabrication of the circuits, all the circuit elements will be similar. So in place of a resistor will be a passive element actually. Resistor will be a passive element. So because of its more power consumption of a direct resistor, we use an active element called as a MOSFET again in order to reduce the power consumption. So here in place of a resistor, we are making use of an nMOS again. The next point, the output is taken from the drain and the input applied between gate and ground. So for this nMOS inverter, output is taken where at the drain terminal of the considered MOSFET and input is applied to the gate and the ground, between the gate and the ground. Resistors are not conveniently produced on the silicon substrate and they occupy excessively large area. So if I use in place of this one a normal resistor, these are not conveniently produced on a silicon substrate and they occupy large area. So a convenient way to solve this problem is to use a depletion mode transistor as the load. So now see here. So I am using a depletion mode transistor in place of a resistor as the load. Hope that is clear. So these are the transfer characteristics of the nMOS inverter. So taking consideration into the constructed nMOS inverter, what we have discussed in the previous slide. See here, the depletion mode device is called a pull-up device. So this is a depletion mode. So this is the symbol for depletion mode. You can differentiate the symbol between depletion mode MOSFET and enhancement mode MOSFET. So this is called as a pull-up device. Why? It is pulling the output towards the supply. And the enhancement mode device is a pull-down transistor. So this is the enhancement mode transistor. This is called as a pull-down device. Why? It is pulling down the output towards the ground. With no current drawn from the output, the currents IDS for both the transistors must be equal. See, the output is ideal, this is not connected to any load, what happens, there will not be any current that is flowing from the output into the devices. In that case, the current that is flowing from supply to the ground between these two transistors must be same, that I am calling it as IDS. For the depletion mode transistor, the gate is connected to the source, so it is always on, and only the characteristic curve VGS is equal to 0 is relevant. See here, for a depletion mode transistor, what is there? This gate is always connected to the source. When gate is always connected to the source, so we have already learned in our starting classes, for a depletion mode transistor, the channel will be already implanted during the manufacturing process itself. So what happens? A small amount of gate voltage directly applied. If VGS is just greater than 0, or for a negative value of VGS also, the transistor will be on. So for VGS is equal to 0, definitely the transistor will be on. So gate is directly connected to the source means what? This is generating a condition of VGS is equal to 0. So in that case, this transistor will be always on. This depletion mode transistor will be always on. Hope that is clear. That is what mentioned here. So what will be the relevant characteristic curve for VGS is equal to 0? For VGS, only for VGS is equal to 0, we have a relevant characteristic curve. So what is that one that is shown here? This one. So for VGS is equal to 0, how the current is changing when VDS is applied between drain and source. Voltage is there, a potential difference creates, how much amount of current is shown by this characteristic curve. Next, to obtain the inverter transfer characteristics, so to obtain the total characteristics of this circuit, we superimpose the VGS is equal to 0 depletion mode characteristic curve on the family of curves for the enhancement mode device. So this VGS is equal to 0 curve of depletion mode when it is superimposed with the, whereas for nMOS enhancement, we have a set of curves for VGS of various values. So this is for VGS is equal to 0.2 volts, and this is for VGS is equal to 0.4 VDD, and this is for VGS is equal to 0.5 VDD. See here they are marked, and whereas this is for VGS of enhancement mode transistor of 0.8 VDD. So when these two are superimposed, we get the total transfer characteristics of this circuit. How? The points of intersection of the curves give the points on the transfer characteristics. So where this transfer characteristic, this characteristic of depletion mode transistor curve is intersecting with the family of curves of enhancement mode transistor. So putting all those intersection points into a graph, we will be getting the transfer characteristics. Hope that is clear. So transfer characteristics of nMOS inverter will look like this. So when you separate, it will be looking like this. This is the overlapping of both the curves, and this one is the exact transfer characteristics what you see. So point at which V out is equal to V in is denoted as V inverse, and it will be noted that transfer characteristics and V inverter can be shifted by variation of the ratio of pull out to pull down resistances denoted by ZPU by ZPD, where Z is determined by the length to width ratio of the transistor. See here, this can be the transfer characteristics of an nMOS inverter. So this can be shifted upwards or this can be shifted downwards by varying a parameter called ZPU by ZPD, that is ratio of pull up by pull down, we call it as. In short, in normal terms to say, the resistance values of a pull up network by pull down network. So which are determined by the length to width ratio. Z is determined by L by W of the device. Length and width are the geometrical parameters of the device which are known to you. So that is what of our interest to calculate the ZPU by ZPD ratio for a nMOS inverter driven by another nMOS inverter. So we have taken into consideration this one. So in order to cascade the inverters without degradation of levels, we are aiming to meet the requirement V in is equal to V out is equal to V inverse. That is in our transfer characteristics, the point at which V out is equal to V in is known as V inverse. So in order to properly cascade these two devices, this is cascading these two devices. V out should be equal to V in should be equal to V inverse. This is the condition we need to achieve. So for equal margins around the inverter, we said V inverse is equal to 0.5 VDD. So this is considered as 0.5 VDD typically. At this point, both the transistors are in saturation. So at this point, what happens? Both this depletion mode transistor will always be in saturation. At the same time, this enhancement mode transistor will also be in saturation. Both are in saturation. In that case, what is the current flowing in these devices is given by IDS is equal to K into W by L into VGS minus VT whole square by 2. This is known to us already in current derivation we have seen. So for a depletion mode transistors, that means for this transistor, we already know VGS is 0. So substituting it here, we get the equation as K into, in place of W by L, that is pull up, no, WPU by LPU, and in place of VT, we are writing it as VTD, represents a depletion. So minus VTD whole square by 2. And in enhancement mode, IDS is equal to K into WPD by LPD, and whereas VGS here now is nothing but the input what I have applied between gate and source, we are considering it to be 0.5 VDD. So that is V inverse minus VT whole square by 2, since VGS is equal to V inverse. So as these two, the same current flows through both the devices, we can equate these two equations resulting in this equation. So when we rearrange the terms with L by W ratio as Z, L by W ratio as Z, and solve it and applying the typical values of V threshold for enhancement mode as 0.2 VDD and for depletion mode as minus 0.6 VDD, and V inverse we have considered it as 0.5 VDD. All this if you substitute in our equation, that will result in a ZPU by ZPD value of 4 by 1, which is a very important typical value for an inverter. For what? For an inverter directly driven by an inverter, that is nothing but an nMOS when it is cascaded with one more nMOS without degrading the performance of the, when we are trying to give an input here, it will generate an output here. So this output should not be degraded when it is given an input here. For that one, what should be the condition for this nMOS to be maintained is ZPU by ZPD should be equal to 4 by 1. So which is nothing but directly affecting the L by W ratios of both the pull up and pull down devices. Nothing but the dimensions of PMOS and NMOS, sorry, not PMOS, depletion mode and enhancement mode transistor should be 4:1. That need to be taken into consideration. Hope this is clear. So based on this topic, there are few lecture level questions that can be answered comfortably by you. Just have a look into these questions. That's all for this topic. Thank you. Happy learning.